double covers SO3. What do I mean by double cover? So it's kind of a new term. Basically what I mean by it is I mean that it's a 2-to-1 map. And by map, whenever I'm talking about groups, I'm always talking about homomorphisms. So it's a 2-to-1 homomorphism. Yeah, so the idea here is remember that we saw that Z2 was actually a normal subgroup of SU2, right? So before, at the very beginning, so yeah, I guess I could say, recall, we wrote down that minus the identity, comma the identity, was actually a normal subgroup of SU2, right? And this guy is actually isomorphic to the group Z2, right? It's just a 0 and 1. And so yeah, we can write exactly one of these short exact sequences down, where we have Z2 hooks on into SU2, and then we can project down into some other group, and it turns out that this other group is exactly SO3. And so the inclusion map's pretty simple, right? We just stick those guys in there. But what is this map pi? So I should say, where pi is a map that takes some u in SU2 to some r, some rotation in SO3 via the relation okay, here's what we're going to do. We're going to take this unitary u, and we are going to conjugate a Pauli operator by it. And this Pauli operator is going to be some Pauli operator that's, or it's some linear combination of Pauli operators that's given by the dot product between the Pauli and some unit vector in R3. Right, so I should say in here is in R3. And what does that do? Well, we know that this is just going to, like from quantum mechanics class, we've seen that whenever we conjugate Paulis by SU2 operations, it just gives us some new linear combination of Paulis, right? So what we end up getting is we end up getting some new linear combination, and that can be related to the old linear combination by just first rotating this vector in. Yeah. So that's the idea. To figure out what the map is, to see what each element of SU2 maps to, take this combination of Paulins, take this unitary, conjugate it, we get something new, write it as a rotation on the original vector. Something that you should notice about this, though, is that plus or minus u, actually, yeah, this is just a note. Note that plus or minus u actually maps to the same rotation, right? It doesn't matter if I throw a +1 or a -1 in front of these guys, because I conjugate, that detail gets washed out, right? Which is exactly reminiscent of the fact that the kernel of this map is the image of this map, which is Z2, right? All of the Z2 structure gets washed out. Or namely, plus or minus 1, both map to the identity. So this is exactly this is exactly what we mean whenever we say it's a double covering, right? Both plus u and minus u map to the same rotation. It's a 2-to-1 map. Yeah, and then I want to say anything else about that. Oh, well, okay. I meant to say that a little bit later, but that's okay. Yeah, because I was going to, so let's connect this with something else here, some other property of SO3. So we noticed so I guess I should write in a big box here, if there's one thing that you take away from this, right? SU2 mod Z2 is isomorphic to SO3. Right? That's sort of the big result. big Lie group, SU2, we construct the small one, SO3. Cool. And so this modding out Z2, it kind of looks like we're taking points out of the group, or maybe more so we're taking 2 points in the group and we're sort of associating them together, we're kind of gluing them together. And this actually does really funny things to the topology of SO3. Namely, yeah, so the resulting group has a totally different, or a slightly different topology than what SU2 had before. And so yeah, we'll see how this is sort of clear. And how one could maybe think, oh, given SO3, by analyzing the topology, we can figure out what the heck this bigger group SU2 was in the first place. If we didn't know that it was SU2. Yeah. So that is kind of the big thing that I want to get across here. Yeah, so before we talked a little bit about, I think Chris talked about connectedness. And so what we'll see from this is that SO3 is not simply connected. Not simply connected. Yeah, so how do we see this? Well, let's sort of try and visualize the geometry of SO3. How can we sort of visualize the space of all transformations in SO3? Well, one way to do it is to note that to denote R in SO3, we need two things, right? We need a direction to rotate about, an axis of rotation, axis, and we need an angle to rotate on. Okay. Furthermore, the other thing that one should note is the fact that if I rotate about the axis n by an angle pi, that's exactly the same as rotating about the axis minus n by an angle minus pi. Or should I say n by minus? Should I erase this guy?
Well, what you had was true. With one minus sign, that's a little less true.
Wait, is this true?
That's also true.
Okay, cool. Sorry. I don't know how to
Pi around any axis.
Yeah, yeah.
Seems
Right.
might
Yeah, yeah. I'm going to move this minus then. I'm going to throw it down there.
Sure.
Yeah. Pi about this axis is the same as pi about this axis, right? That's the idea. Yeah. Great. Okay. Yeah. And so the idea is that what we're going to visualize the space SO3 as a sphere, or sorry, not a sphere, a ball. A ball in 3 dimensions that has radius pi. And we can specify 3 coordinate axes. That's one. And so a point within this ball represents a rotation, right? Because the distance away is the angle, and then the orientation denotes the direction. And notice that because of this final fact, actually we should associate antipodal points on the sphere, right? The North Pole is associated with the South Pole, because a rotation about pi in this direction is the same as a rotation about pi in this direction. Okay, so now we want to know something about simply connectedness. And remember, simply connectedness has something to do with, if I write a loop down in this space, can I always contract the loop to a point? Or is it less trivial than that? If something is simply connected, it means that you can always contract the loop to a point. So we can consider, consider the following loop. Let's draw a loop where we say start at the origin, move up to the North Pole, but the North Pole is associated with the South Pole. So now let's go here, and let's move back to the origin. So we have this funny curve. It's a closed loop in space SF3. And now let's ask, if we deform this loop, can I contract it to a point? Well, you might think, okay, well, let's just try and move these 2 points together. But you notice that the moment that you deform this point over this way, this point, they're associated, they're the same point. So this point gets deformed over this one. And then we see this kind of funny, we can draw this kind of new curve that we get from this, which we see we're nowhere close bringing the 2 points together, right? We're nowhere near being able to contract this guy. So this is a non-contractible loop. Non-contractible. However, if I do another loop, it's very similar, but instead I wind around twice. So let's start at the origin, move up to some point. We end up at the South Pole. Move back. I'm sorry. Move back up to the North Pole. We come back to some other point, and then move back to the origin. So we wind around twice. Now one notices that as I displace this guy,
It is one.
yeah.
Yes.
So maybe I should make it a little more obvious than this one.
Which dot is which?
Yeah, let's use the colors. So I'm saying, yeah, let's draw one here, and one here. I first move, yeah. So I first move up to here, then I'm down here at the South Pole. Then let's just say I move over here. Then I'm down here. So I guess I should say this point is associated with this point. And so on and so forth for the other two. And now one sees that we do have this property that just by moving the orange points, we move both of them, right? A little bit closer. And so one sees that eventually we could just contract this whole thing to 2 points. A point on one side, a point on the other side, where we sort of overlay the orange and white points. And we just have one sort of closed loop. Yeah, so this is the contractible loop. Anyways,
So before you joined the orange and white though, you could have just moved the loop over. And that makes it, because that is just one point.
just move the loop to the surface of the
Right, so
sphere.
don't quite take orange and white to the same point. So
Yeah.
maybe draw that little
Oh, okay.
when they're close, but they're not joined.
Wait, so you're saying just move them like this? I'm sorry, what do you mean?
Yeah, so here you contracted things a little much, so let's instead think about this.
Yeah.
Contract a little bit.
Okay.
And this is the same point as this.
Yeah.
Then you can just move this over.
Oh, I see.
And that's,
And then you don't have to just have one point
then
on the
there's
surface.
no pinching thing. Yeah.
Okay. Yeah. No, it's okay. It's smaller. Okay. Yeah, sure. That's fine. That also works. Yes. Okay, great. Yeah. So anyway, what one could convince themselves of is that these are the only two types of loops that one could draw. Contractible loops and one possible non-contractible loop. So this is related to the subject that's called homotopy, which I'm sure like everyone here has probably at least heard of. People call the group of all curves that one can write down, all closed loops that one can write down in some space as the fundamental group, is equivalent to saying that this fundamental group of SO3 is actually equal to Z2, which is intimately related to exactly the Z2 that we mod out here in order to get the SO3 structure.
Austin,
Yeah.
could you talk about the non-contractible loop again? Can you tell me how that is not contractible?
Yeah. So the idea is that I kind of only have these 2 points on the surface here, right? So my point was that as soon as I
Okay.
start to translate this guy to the right, this guy automatically moves to the left, right? Because these 2 points are the same point actually. So by moving this point, I move this guy too, because they're one and the same. So that's the idea. Yeah, I could never bring them to one single point, right? Bring this loop to one single point. Yeah.
So I think this begs the question, we talked about this fundamental group being Z2, and it's related to the fact that Z2 is the normal subgroup of SU2 that we mod out to get SO3.
Yeah.
Why is SU2 so special? Why is the fact that
Yeah.
SO3 is the quotient group of SU2
Yeah.
related to its topology? 'Cause I can imagine I just have lots of groups which are related maybe
Uh-huh.
by I mod out something else and I get another group.
Yeah.
Is it always is there something, maybe the question should be asked,
Yeah.
is there something above SU3? Did I mod something out of SU3? And if I talk about that, SU2, sorry. Yeah, did SU2 come from something
Yeah,
something
exactly.
bigger?
Yeah, no, exactly.
And
Yeah.
that's
And
what
that's,
is
yeah.
topological defect on SU2 as well?
Exactly. Yeah. Did SU2 come from? No. So SU2 is simply connected,
SU3
right?
is-
So yeah. So I think that's the thing is that SU2 kind of is already as big as it can get. I guess is the idea. Yeah. But I mean, but this is something that will be a general trend. Is that whenever we, by like to construct, so this is kind of the next topic. To construct any one of these Lie groups, which is generated by a simple Lie algebra, what we do is we first look for the largest Lie group that is generated by that Lie algebra. And this largest Lie group, which is called the universal cover, will always be simply connected. And by modding out centers of this universal cover, we can reproduce any, well, I guess this universal cover or its real forms. We can reproduce any Lie group that has this sort of simple Lie algebra, but it will have something like, it will have some funny topology to it. It's
So I'm
something
looking
that's
for
not
the-
going to be simply connected.
I'm looking for this big guy that doesn't have these weird topological defects on it.
Huh?
Can I think about it like that? Like I'm looking for this big guy that doesn't
Yeah,
have
exactly.
any
Yeah.
topological
Huh? Yeah.
defects to it.
Exactly. Yeah. You're looking for this big guy that has, that doesn't have any of this funny topology. You're looking for a big guy that's simply connected. Right? And then by modding out these normal subgroups, you end up introducing, holes in your topology.
Can you remind me again, how does spin relate to this? Because I thought spin was like a universal cover.
Yeah. We're gonna get to that. Yeah.
Austin, good
Yeah.
question. So from this construction that you've shown us, can we conclude that SO3 is not simply connected?
Yes. Yeah. I think that all you really have to see is this one guy, and you say, yes, a loop that cannot be contracted to a point. Bam, not simply connected.
So does it mean that the existence of a loop that is not contractible
Mhm.
implies that the group is not simply connected?
Yes.
the definition.
That's the definition. Yeah.
Okay.
Yeah.
And it's an existence, like even if one exists, the group is not simply connected.
Yeah, exactly. Yeah. Yeah, but then, calculating this fundamental group is a little more hard, right? Because you have to think of all possible loops that you can draw in space. Yeah, cool. So I guess I have like 15 minutes left or something? Do we go to 5:15? 5:20? Okay, cool, yeah, I can wrap up in 20 minutes. That's good. Yeah. So awesome. So this is kind of the fundamental idea, right? The idea is that we always want to find this thing where we have. Well, I guess I just erased it. But so we want the largest such Lie group. Which we call G hat. And this is what's called a universal cover. Yeah. And so then the idea is that we're just going to think about normal subgroups of the universal cover. And we're going to mod those guys out and get some other Lie group, G or G prime. Right. Cool. And so this universal cover will have the largest, I guess I could remark that it has the largest center. Yeah. There is also a group which has the smallest center. The Lie group with the smallest center. And by the smallest center, I mean it's trivial. Meaning there is no center. Is what's called add G. Where you can sort of think of add G as something where, like, I don't know, if I have G hat, I can map to add G hat. By the mapping, I take G, which is something there, and I map it to G suspend evaluation, G inverse. Okay, sort of suspend evaluation on some element of the Lie algebra. And you notice that this thing is, agnostic to the existence of the center because of the fact that it shows up twice, right? So you have element of the center's inverse. Everything commutes, so they just annihilate each other. Yeah. But anyway, yeah, the universal cover is kind of the big thing. Yeah. And so we see that if we have the universal cover and we find all of its normal subgroups and we just mod them out, taking the universal cover in all of its real forms, we can construct every possible Lie group that has this same simple Lie algebra. Yeah, and so let's see kind of how that works. So I'll kind of just give a list of these things going back to, but we won't really talk about the exceptions, I guess. And I don't know if the exceptions, are they necessarily generated by simple Lie algebras? Yes? Okay, so yeah, minus the exceptions, we will have the full classification, right? I'll give you the universal covers. Yeah, so let's make a kind of a table first. Lie group. So this is just going to be the table that allows us to find all the covers. Univ cover. And then centers. I guess the center of the universal cover. And we can also mod out any subgroup of the center, right? Any subgroup of the center is also going to be some central normal subgroup.
But technically what you're going to put in the first column, those are called classical.
Yeah, classical Lie groups, exactly.
Unfortunately, not to say that they're not quality.
Yeah, sure. Yeah. So we talked about these classical Lie groups. Yeah, I guess I should. So the first one is AN, which is SL n plus 1 comma C. Its universal cover is actually itself. This is the largest such group generated by this simple Lie algebra. What is its center? Well, one can argue that everything in the center should be something that's proportional to the identity. Something we can use with everything. I guess, I don't know, maybe you could argue that using this Shearsonge we'll talk about. Maybe. I suppose. representations. But the idea is SL, these guys are special, so they have determinant 1, right? So if I consider here, I'll just write down the answer for you. It's going to be Zn plus 1. But let's see why that is. Why? Well, the determinant of some number times the identity should be equal to 1, right? If this is supposed to be a special linear transformation, this determinant should be 1. And we know just by the fact that this is a n plus 1 by n plus 1 dimensional matrix, we get that this tells us just by rule properties of determinants, omega to the n plus 1 should be equal to 1. So omega should be equal to e to the I 2 pi m divided by n plus 1 for some n being an integer. So we see that the center is furthermore, there's this guy B, and this is SO2 n plus 1 times C. Its universal cover is something that's kind of funny, and I'll kind of give a brief discussion of this at the end if I have the time. But this is called the spin group. Spin 2. Plus 1. Yeah, sorry. yeah. Spin 2n plus 1. Yeah. What is the center of spin 2n plus 1? Well, this is just Z2. Why? Well, I won't really discuss this. And I don't really exactly know the calculations. Anyway, yeah, and then we have Cn. Right? Cn was sp2n, right, which is this funny symplectic group. This is kind of like the compact version of the symplectic group. Its universal cover is actually itself. And its center will also be Z2. Yeah, exactly. And why is that? Well, because if we just take the same argument that everything in the center should be some number times the identity, remember that the definition was that we preserve this symplectic matrix. And so this would mean that omega squares to 1. So omega equals e to the I n pi. Or I guess n pi. For n.
So you didn't need to restrict yourself to the compact form. If you're thinking complexify for A and B, you might as well consider the complexify as the two.
Sure.
So
Okay, I guess it's just a. Looks like a.
And just to make the treatment parallel, right? So you choose whether or not you're going to consider the complex form
Yeah.
or its maximum compact subgroup.
Okay.
So for A and B, you chose to think of them as complex. And to really do the analogous thing, just consider the complex SP2 on this level.
Okay. Okay. So is it just okay? Yeah. I guess yeah, because this guy isn't necessarily compact.
Right.
Yeah.
But it has
So then,
the same.
I was gonna say, is it just like miraculous that all of these things end up having discrete centers? Because I mean, before it was like it seemed. I mean, that thing that we didn't prove at the beginning there, which was something that said that if e to the g is compact, then these guys will always be finite discrete groups. Yeah. But I guess it just so happens that even in the case whenever these things aren't compact, they also turn out to be finite discrete.
Right,
It's
because
good
you
enough.
can calculate them explicitly.
Okay. Yeah.
Yeah, those are all fine.
Yeah.
Finite.
Yeah. 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 It's good. Yeah.
So would you put a comma C for me?
Oh yeah. Sure. Yeah. Totally right. Actual first place. So I don't know why. Getting so much about that.
Austin, what is the spin 2n plus 1 group?
I will get to that afterwards. Yeah.
Okay.
I'll talk about that shortly. But just know that there is some group which turns out to be the universal cover of SO, which is called the spin group. Yeah, and we'll see it again here in the case of Dn, which was SO2 in comma C. Right. Turns out that its universal cover is spin 2n. And it has centers. Well, actually, it can have two different centers. The first one is Z2 cross Z2. If 2n is equal to 0 mod 4, and it's Z4 if 2n is equal to 2 mod 4. And again, yeah, I haven't shown this for myself, so I don't necessarily know how well it would show. But I mean, I guess it kind of gives some idea. Regardless, yeah, it's, I'm not quite as familiar with these spin groups. Yeah, so quick note on spin. Let's just talk about what the heck this thing is. Yeah, so how do I start this? Yeah, so there's something called spin in, and the thing that you should think about whenever you see the spin in is it double covers SON. Okay. So some facts about it. It's generated by linear combinations of quadratic elements of a Clifford algebra. Is a new term. Let's see exactly what it is. So for a Clifford algebra, the idea is that given some space with some metric, given a manifold M with metric G mu nu. We have the Clifford algebra. I guess I could say, I don't know, do people write this? Cliff N, which is essentially just the set of operators gamma mu, such that if I take anti-commutators of them, I get twice the matrix elements of my metric. So anti-commutators of these guys give me twice the matrix elements of the metric. We know of one simple example that we work with all the time in quantum information, which is Pauli operators, right? Pauli operators satisfy an anti-commutation relation. So we can think of Pauli operators as a Clifford algebra on Euclidean 2-space. Okay, so this is the Clifford algebra, but I guess I should say what this Clifford algebra is on. The Clifford algebra.
And so the comment you just made about Pauli's,
Yeah,
does that mean that spin 3 is the same as SU2?
it does indeed. Yep, exactly. Yeah, and this is, yeah, probably like the last thing that I was maybe going to get to, which is these accidental isomorphisms, but I may not have time to talk about them. But yeah, exactly. Spin 3 is exactly isomorphic. So this is exactly this thing Andrew's comment about, like, Yeah, like you kind of knew all along that the universal cover was going to be these spin guys, but then you were like, what the hell? Like, didn't you just say that SU2 is the universal cover? And it turns out that for like low dimensions, there's turned out to be a lot of isomorphisms between spin groups and, or at least the Lie algebras generating the spin groups, and the Lie algebras generating, say, SU2, SO3, et cetera, et cetera. I might write those down at the very end. These funny accidental isomorphisms, as they call it. Oh yeah. So the Clifford algebra for spin in is n-dimensional Euclidean space. So i.e., we just have a very simple Clifford algebra. Gamma mu is just twice delta mu nu. Because the metric is just one. Yeah, okay, so then what do these guys look like? So then we can write spin in as elements that look like this. E to the 1/2 A alpha beta gamma alpha gamma beta, such that A alpha beta equals minus A beta alpha. So yeah, as I said, they're generated by linear combinations of quadratic elements in the Clifford algebra. Yep. And yeah, this anti-symmetry property has to hold, right? So that if I sum over these guys, I don't end up canceling things out. And just add things together. Anyway, yeah. So wonderful. There's another point. Oh yeah, the double cover. Yeah. How could one forget?
So technically this needs to be a little amended.
Oh, okay.
So the quadratic terms,
Okay.
only quadratics can only make spin 2ends.
Okay.
So yeah, it's n-dimensional manifold M, n-dimensional manifold M.
Okay.
That will make a spin 2n. And you make this, so all of these things we said are actually spin 2n.
Okay.
And so then you would ask, well then how do you make this spin 2n plus 1? You include quadratic and
Linear terms. Okay.
so only quadratic will only make a spin 2n.
Yeah, but spin n still double cover. Yeah, so that's spin 2n. Yeah, I guess then spin 2n plus 1. I'll just say, add something like a b alpha gamma alpha in the exponential. Yeah, and so then what is the double cover? Well, we basically just do exactly what we did with Pauli operators. We do exactly what we did with Pauli operators. So it's the following. So it's always a double cover. So we have Z2 hooks into spin in, maps down into SON. The idea is we let T be an element of spin in, and R an element of SON. Right, then the map works as follows. You just take T and T inverse, and you conjugate some vector of some vector of entries in the, or some vector of elements of the Clifford algebra. And what this ends up giving you is exactly some rotation on this thing. And it actually turns out that this R is actually related to this A that one finds from this T. R is actually equal to e to the A. And you might say, ah, this makes a heck of a lot of sense, right? Because of the fact that this is an antisymmetric matrix. And I know that the generators of SO3 should be antisymmetric matrices. Cool. Yeah. So that's what the heck the spin thing is. Kind of a very brief introduction.
Another quick
I
one.
really know how much.
So
Okay.
if R is going to be e to the A,
Yeah.
then you need a quarter in front of the A. So Arlene back to the quadratic Hamiltonian,
Okay.
that needs to be 1 over 4.
This should be a 4?
Yeah.
Okay.
So that's,
What can I add on the A? to make
you can
it-
put a 2 next to that A if you
Let's see.
just in case someone does the exercise.
Yeah, okay. Sure.
Starts pulling the hair out.
Yeah. Okay. Yeah, okay, great. Yeah, okay, great. And then so then yes, from all of these universal covers, classical V groups, using the centers, we can indeed write down every possible V group generated by the single algebra. And it goes as follows. So we could just write down like one set, one could write down a whole bunch of tables, these classification tables. We'll just kind of begin to write down one. We won't really fill out all of the entries. But yeah, for instance, we could consider, say, A3. On the top of A3, I will write it in all of its real forms. Okay. A3 will have SL4, comma C. Right. What are the other real forms? SL4, comma R. SU4. SU3, comma 1. SU2, comma 2. And SU4. Okay, A3. Different centers. Well, there's sort of, don't mod anything out. Z1. Z2, and then Z4 is the whole center, right? So Z2 is just the central subgroup. And then one just fills out the table by modding these guys out of all of these real forms. So for instance, we have SL4, comma C here. We have SL4, comma C mod Z2 here. And then we have SL4, comma C mod Z4 here. Notice that this guy will always, this top entry will always be the universal cover. And this bottom entry, since there is no longer a center left over for the group to have, this will always be add G. And then one could, try big, etc. Yeah. Yeah, so that is basically it. I guess I'll just say like, one thing that I could say is as I mentioned before, there's this notion of these accidental isomorphisms, right? We noticed that for some of these guys, the Lie algebras that generate them, sorry, not these guys, but the A and B, before we had, yeah. Yeah, so remember that we had A in, B in, C in, D in were our classical Lie groups, right? But it turns out that for small values of n, a lot of these guys are isomorphic to each other. And these are the so-called accidental isomorphisms. And the accidental isomorphisms are as follows. Turns out that SO3 is actually isomorphic to SU2, which is actually isomorphic to SP2. Furthermore, SP4 is isomorphic to SO5. SO2 is simple, actually. SO4 is abelian. Is simple.
Yeah, they're all simple.
Oh. Why do I have the simple? I don't know. Yeah, I guess I just don't understand. SO4 isomorphic to SU2 plus SU2. And then finally, SO6 is isomorphic to SU4. Yeah, and so then this means, you know, the corresponding isomorphism here. D2, this one tells us that D2 is isomorphic to C2. D1 isomorphic to U1. And U1 phases. And D2 isomorphic to A1 by A1. And finally D3 is isomorphic to A3. Yeah. These are the accidental isomorphisms. And so to be clear, in order to avoid these, people usually enumerate these things in a certain order. Basically, we say AN is like something that is unique whenever we define 1 being less. We start at 1. BN is unique if we start at 2. CN will be unique if we start at 3. And DN will be unique if we start at 4. And that's it.
So these really are accidental and only exist in small dimensions.
Yeah, exactly. Yeah, exactly. So so it turns, this is exactly, I mean, this one is the one that we really saw though, right? In the sense that SU2 was the double cover, or was in fact the universal cover of SO3. However, whenever we move up to larger dimensions, it's not that SUN minus 1 is going to be the double cover of SO. You have to move to spin groups. Yeah, you could furthermore insert the spin groups in for the algebras generating the SOs too. It should have the same. Should be the same.
Don't let the name accident fool you. The existence of the isomorphisms can make you do fantastic things. Right? So this says there exists 5 really special isomorphisms.
Yeah, sure.
So, not to sweep them under the rug.
Yeah. Yeah. I guess I don't know. Does this one show up in like quantum information somehow?
So I know when you do quantum field theory, and
Okay.
say, we live in 3 space
Yeah.
plus 1 time.
Yeah.
What do you just use it in match gates or something?
Yeah, that's what I said. Yeah, something along the lines
That's
of
it.
that.
Right. Match gates too.
Match gates.
That's it.
That last one.
That's the same one.
That last one there.
I've never seen that one.
Yeah.
Wait. No, that's not. No, that's the answer.
Physics we use SU4.
Cool. Yeah. So that is all.